Good morning, everyone. Our very first speaker is Nasibeh Arabameri. Where are you? There she is. Okay, she is a fourth-year PhD candidate in microbiology. Her research focuses on understanding the hidden diversity within bacterial biofilms using cutting-edge single-cell RNA sequencing techniques. She's particularly interested in how microbial communities adapt, survive, and tolerate treatment in chronic infections. When she's not in the lab, she loves hiking, gardening, and exploring new creative projects. Please join me in welcoming her to the podium.
A slimy layer on our teeth, a wound that won't heal, a slippery rock in a riverbed, or a clogged pipe that costs industries billions of dollars to fix. What do they have in common? They all have biofilms. Biofilms are organized bacterial community wrapped in a protective layer. They are resilient, sticky, and surprisingly strategic. We tend to think of bacteria as if they are lone cells floating in a liquid. But in reality, bacteria may live together as communities. And together, they are far more powerful than alone. These biofilms cost the world about $4 trillion every year. This is more than GDP of Germany. 70% of this comes from industry, 19% from healthcare, and 11% from agriculture. Just think about it. This is the money that we could use to build hospitals, fund research, and education. But beyond the dollars are the real human costs. Patients who suffer from chronic infections because our drugs don't work. In fact, the World Health Organization predicted that by 2050, infectious disease will surpass cancer as the leading cause of death, claiming up to 10 million lives per year. It's devastating, and biofilms are the major contributor to this crisis. So what are these biofilms exactly? When we imagine bacteria, we often think of individual cells swimming freely, right? But that's not how they live. In reality, bacteria attach to a surface and produce this glue-like material that protect them from threats. And these biofilms can live almost everywhere. They are on our teeth and our guts, on medical implants, and even in space stations. So what's their secret weapon? It's their diversity. Just like a human society, each cell in a biofilm takes on a different role. Some build, some protect, some adapt, and this teamwork makes them up to 1,000 times more tolerant to antibiotics compared to those individual cells. And that's why 80% of infections are biofilm-based. So the question is that why treatments fail on biofilms? Well, it's because we are using the wrong model. See, most antibiotics are designed for these free-floating cells. But in reality, that's not how bacteria live. They live in communities, biofilms. They're like cities, they are complex, interactive, and structured. And so it's like trying to understand the city by watching just one person. You miss the big picture, the interactions, the division of labor. And even if we want to study the right model, we can't because we don't have the tools to do that. So we know there is diversity in these biofilms, and that's how they survive very well, but we don't know much about it. We don't know what that means and what these cells are doing in a biofilm. And that's where my research comes in. I developed a method to zoom in on biofilms and look at gene expression of individual cells. It's called single-cell RNA sequencing. It's a high-throughput technique that lets us see for the first time who is doing what in a biofilm. Imagine giving an ID card to each bacterium based on their role. So with this method, now we're able to see who's the builder, who's the defender, who's the teacher, etc. And what's even cooler is that we can map back where each of these individual cells are located in the biofilm. So then we can use that information to find the weak spots in biofilms and design smarter, more precise treatments. So then we can break these communities apart. By understanding biofilms at a single-cell level, we're not just curing infections. we are making a world that's smarter, cleaner, and more efficient. Diversity is nature's survival strategy. Ecosystems thrive through diversity. Communities grow stronger with it, and biomes endure because of it. But if we keep designing treatments for bacteria as if they're all the same, we'll keep failing because we're fighting the wrong war. But if we work with this complexity, if we understand it, we can design better drugs, we can protect our infrastructures, and prepare for a future where no bacteria win. Thank you.